Hello, my name is Nicole Virgilio, and this summer I was a part of the REU for Chemical Engineering here at the University of Florida. My project was focused on the synthesis of well-defined heterogeneous catalysts for use in the para-hydrogen-induced hydrogenation reaction of propyne. Before I get into the project, I'll introduce myself a bit more. I'm a student here at UF going into my fourth year studying chemical engineering, and I'm planning on graduating this coming May. My mentors this summer were Dr. Helena Hagelin-Weaver, and my PhD student mentors were Han-Chin Zhao and Li Yin Xiao. To give a brief background of what we're working on, the heterogeneous name comes from the fact that the catalysts are solid while the reactants are fluids. Our catalysts have two parts, the active metal, which is a site of interaction, and the support that adds efficiency and strength to the catalyst. The active metal is typically a transitional metal like iridium and rhodium. The supports that we use are metal oxides like titania and ceria. Our aim is to produce well-defined shapes such as ceria octahedra and titania nanorods. This helps us to identify structure-activity relationships and have consistent metal support interactions, since this can influence the properties of the metal. The first catalyst that I worked with was the 0.5% iridium on titania. With this iridium catalyst, our aim was to use three types of titania support to compare their characteristics. These three supports were the rutile nanorod, which we synthesized in lab, rutile nanoparticles, and anatase, both of which were bought commercially. To deposit the iridium onto the catalyst, we used precipitation with iridium chloride and urea. The second catalyst that I worked with was 3% rhodium on ceria octahedra, which we synthesized and characterized, then worked to add an overcoating of zirconia with atomic layer deposition. Now, what are these catalysts used for? The overall goal is to use these catalysts in enhancing NMR signals for diagnostic imaging techniques such as MRI. To do this, our catalysts are used in propyne hydrogenation with para-hydrogen, a special kind of hydrogen molecule in which the two hydrogen atoms have opposite spin directions. This reaction is performed by our collaborators in the chemistry department, the Dr. Bowers group. Since it is designed as a continuous flow reaction, it creates continuous flow of hyperpolarized signals, which can be used for in vivo use in MRI applications. This would be the main advantage that heterogeneous catalysts have over homogeneous catalysts. Since the catalyst and product are at different phases, separation is more straightforward, and the toxic transition metals can be removed to a safe level. Here are some of the synthesis techniques that I've learned about this summer, starting with hydrothermal synthesis, which just involves mixing reactants in solutions and placing the mixture in the oven for up to even 24 hours. Incipient wetness impregnation is a technique that I use to add the rhodium onto the ceria octahedra, where we add the smallest amount of active metal in solution possible, stir to mix well, and then heat the catalyst to evaporate the solvent. Atomic layer deposition is a cyclical vapor phase technique where an active metal precursor is introduced to the chamber for a few seconds at a time so it can react with the support. Here are a few of the characterization techniques that I've learned about this summer. Transmission electron microscopy, TEM, allows us to look at the structure and size of the support and allows us to see if a layer of metal was created onto the support. X-ray diffraction, or XRD, gives us information about the crystal structure by looking for characteristic peaks of each type, like, for example, the anatase in this graph below. The one above is of a catalyst that we have made in lab, and below is a reference titania anatase so that we can compare the peaks. BET, or Bronner, Emmett, and Teller surface area measurements give us a specific surface area per gram, an important property of catalysts. Temperature programmed reduction, shown in this graph below, allows us to analyze reducibility of the catalyst and better understand the surface chemistry. Chemisorption, which we performed with carbon monoxide, helps us quantify the number of active sites present in our catalyst. So for example, 2.11% dispersion. And finally, I would like to thank everyone who made this experience possible for me, starting with the NSF and UF for funding this project, my mentors, Dr. Hagelin Weaver, Hanshin Zhao, and Li Yin Xiao, as well as our collaborators in Professor Bauer's group.